So we're going to talk about our NEX, OpenNEX platforms. So last time I talked about NEX Sandbox. Today I'm going to actually talk about NEX or OpenNEX on Amazon Web Services. AWS is commercial cloud. So everyone has a credit card. You can actually open an account on AWS and can you start to use it. Very convenient. All right. So actually, this is our tutorial from 2 years ago, from 2014. My colleague Andy Michaelis, he actually already gave a talk about how to actually you can launch a AWS instance. So very basic, but very comprehensive. So if you don't know how to actually open an account on AWS, I also recommend you actually go visit our YouTube channel, watch his talk. All right. So if you already get the account on AWS, so if you log in, this is what you get, right? So I want you to go to the EC2, basically virtual servers. This is the Ec2 Dashboard, and I want you to launch an instance based upon a community AMI. So basically, we already generate a virtual machine or a template, or saved as AMI. So you can just directly use our virtual machine. So click on our community AMIs and type OpenNEX_workshop in this search box, and it should actually bring up this AMI. So you can select it. Now, so basically, the system asks you to choose instance type. So basically, how many CPUs you're going to use in storage, and about network performances. So for some reason, I don't know. For some reason, I don't know. I don't understand. So they won't allow you to choose those T2 those types, but it's okay. I mean, I don't want to choose the micro instance because it has network performance very low. It's cheap, or maybe free, but the network performance is too low. So I choose this a little bit higher. So, but it's up to you. You can choose whatever you want. And after you do that, you can review and launch. It's going to ask you to choose some key pair, those things. So I'm going to skip those things, because it was already in Andy's talk. So basically, and you launch the virtual machine. Now it's running, so you can log into it. This is the public DNS, right? The public IP. You can log into the virtual machine now. And this is like something like this. You can SSH to your virtual machine, and you get something like this. Well, the first time they may ask you to add, some like this server to your the known host or something like that, and yeah. So, all right. So once you log in, well, it's under your home directory, right? You can do ls. You will see actually we already have 3 demos there. I'll talk about this demo of LOCA, right? But you can also actually take a look and see, find /media/ you will find our NASA NEX. So basically, we're actually kind of mount that NAS data set already there. So do a very LS, you can see there are actually many data sets, not just climate data sets, because we're NASA, we have remote sensing data sets as well. So anyway, so today we're going to use LOCA, of course. So let's change directly into demo sim5_LOCA, and I have actually two subdirectory or folders there. We're going to change into New York City. Again, you can do a ls, and this is the basic the scripts or Python code we're going to use. Well, I have to say, these codes are just, or scripts are just provide as examples. They're not, too, I mean, the quality are okay, but it's not, super, professional. So I know some of you are really, really good programmers. So just don't, if you read those codes and you found something interesting or funny, don't laugh. I know they can be improved. So if I have time. So anyway, so yeah, there may be some bugs, but it's okay. So you can improve it. I'm sure you can do a better job. All right. So the first topic is how are we going to actually extract time series from LOCA dataset just for this particular place, New York City, right? So the way is just you can just run this called the run_dump the shell script. All the the magic happens in this Python script called dump_day_climate.py. So basically, that's the place you do the heavy-duty job. But the script itself actually is smart enough to basically form those input data and to fit in this script. Now, some of you may notice, well, this is actually the original data path, right? So you can go actually follow this link and then to look at those original LOCA data. They're in netcdf file format. So if you know netcdf format, you know you can actually use ncdump or those tools. You can get a lot of information from the header, from headers. But if you don't know, just let you know that netcdf is a very, very common scientific data format. You should read or search it online and learn a little bit about netcdf. All right. So there's one thing I want to talk about this dump, day_climate.py. So it's not supposed to be there, but we actually hard coded something there. So let's see if you want change, because when you run the script, you didn't specify where you want to dump the data, but the magic happens here. So if you want to change the location to somewhere you're interested, you can just go to this file, or you can actually put it in as arguments, but you can still go to the file and change those default locations. So that happens in that dump_day_climate.py script. All right. So all these files take some time to actually run the time series. So actually, I already did extract the time series for New York City for you. So if you go to pick the CCSM4, and you will see there are several text files there. Open one of them. This is actually Precipitation. You will read like the first 4 lines, which is some headers, indicate where we wanted to look at the data, and the data actually from the LOCA files are actually from these grid cells. Anyway, so notice for Precipitation, the current units are actually millimeter per second. So you want to actually scale these values by 3600 times 24 hours, right? So and convert that unit back to millimeter per day. So anyway, all right. So now we have the data. We have Precipitation, we have Tmax, and we have Tmin. So you can look at the data. So Tmax, Tmin, and Precipitation. So the first thing you would notice, well, is actually clearly we have the kind of like interesting or increasing trend, warming trend of the temperature, both of Tmax and Tmin. We're going to get in there. So anyway, so that's probably the first thing you notice. For Precipitation, it's a little bit harder to notice any particular trend, but pretty stable. But you notice there are some extremes, right? So that's actually the beauty of LOCA. So you're trying to mimic, the daily climate variability, extremes, basically what I'm trying to talk. Now, I have to say, I didn't actually plot all these everyday data because it won't, there's some issue of the backend, the Python backend. It won't allow me to actually plot all the data, so I have to pick, like, plot the data for every five days. So if you go to you know, the Python script, don't be surprised if you see something like this. Anyway, so well, you might change this, or you can try different the backend if you have time. All right. So now, because we have the time series, we can do a little more analysis, right? So this one is we're trying to count extreme temperature days. So basically, how many days of the year actually you have Tmax greater than 90 degree, Tmax greater than 100 degree, and this is for minimum temperature, which is it's really cold days, basically less than 32 degree Fahrenheit. So interesting, you probably already see this, right? So for New York City, currently we probably have around 20 days, you know, above 90 degree every year. This is the current, you know, condition. But by the end of this century, by this model at least, we're going to have about 80 days above 90 degree. And for now, we don't really have any days above, well, let's see, we rarely have days of temperature above 100 degree in New York City, but by the end of the century, we're going to have about 20 days. So, of course, the winter is not going to be that cold on average, maybe, or daily. So anyway, so looks like, you know, the point of this graph is like suggests New York City is going to, in terms of temperature, is going to be a lot more like, I don't know, somewhere in Florida in, you know, 50 years or 80 years. So this is another way you can look at the temperature data. What we call is called the heat waves. So we define, the heat wave is defined as a period of 3 or more days, consecutive days when you have temperature or T maximum about 90 degree Fahrenheit. So again, you see this increase of the numbers of the heat waves, right? From currently about 2 to around 8 heat waves by the end of the century. Not only the number of the heat wave changed, but also because the intensity also changed. That means either the heat wave, the period will be elongated. You have, you know, instead of just 3 days, it's going to be 4 days or 5 days, or the, you know, the average temperature for those heat waves will be hotter, or both, right? So that's another way to look at those climate extremes. Okay, so now we're looking at extreme precipitation days. The upper panel shows the number of days when precipitation is greater than 1 inch. The middle panel shows 2 inches, and the bottom shows precipitation greater than 4 inches. So it's really hard to see if there's a significant trend in terms of precipitation extremes from this data. So especially for you know, 4 inches, we don't see, you know, significant changes. There, you know, some happen in the past, there's some in the future. The only panel is this one. I mean, looks like the precipitation above 1 inches, there's very slight changes. So anyway, so it's not very dramatic, not very significant to my eyes. Anyway, but this is the way you look at how extreme temperatures, extreme precipitation changes. So, yeah, that's a very basic analysis. Now, I just mentioned like we have multiple data sets, not just the LOCA. We also have another data set called Global Daily Downscale Climate Projections, called GDDP. So we have both of them on AWS or on any other NEX platforms. So you can actually also do a quick comparison. Both of these data sets, they have very similar format. In addition, in terms of, they are all in this netcdf format, and also have very similar metadata. So you can use the Python script provide for LOCA, do the same thing and to analyze the GDDP data. And you actually can compare them. So I actually, for those scripts, there's a comparison option. You can turn on those options. So you can plot LOCA and GDDP side by side or on top of each other, and you can do some comparison. So let's see, once you plot them, at least for New York City, for temperature, they're actually pretty similar. I would say very similar. The only difference I notice here is, it seems like LOCA is more extreme, slightly, but otherwise it's pretty similar. For precipitation, they're also similar. Of course, we're not talking about one-to-one correlation, those things. We're talking about statistical occurrence about extremes, or some the maximum, minimum, those things. But so to my eye, they're pretty much comparable. So this is just for New York City, one place. So, and this is like the extreme temperature days. Yeah, as I said, well, the days about 90 degrees, pretty much the same. In terms of days about 100 degrees, GDDP is a little bit lower. So LOCA appears to be a little bit more extreme. So minimum temperature is pretty much the same thing. Yeah, there's a heat wave, very similar results. Precipitation. So yeah, it's hard to tell. It's just like, I would call them statistically pretty comparable. Of course, you can notice sometimes when GDDP shows extreme precipitation sometime, but LOCA shows on different time period. But that's not the point. The point is like the frequency or the magnitude of those extreme precipitations appears here to be pretty similar in terms of the characteristics. So yeah, I think that's about this hands-on example. So to wrap up, so today we learned what the LOCA data sets, which is downscaled simplified climate projections that actually especially developed to preserve the characteristics of daily climate extremes and at local spatial scales, right? So by the time you watch this video, I believe LOCA is publicly released. So now what I'm trying to say is now LOCA can be accessed on OpenNEX on AWS. All right. So we also provide a hands-on example how to analyze climate extremes of New York City in the future. So as I said before, you can modify that example and apply it to somewhere else. Or you can actually do more comparison between GDDP and LOCA. Or we have another one, DCP30, on the same platform. We actually have I have the code for how do you actually convert for that US folder. You can convert daily to monthly data and compare it with DCP30. That's another story. Maybe I'll talk about it later. Anyway, so that's about today's talk. So yeah, as before, thank you very much for watching this video. And stay tuned. We're going to actually generate more talks. All right. Thank you very much. Bye-bye.